Okay, so here's a sample data analysis question from the IB. These data analysis questions can be on basically any topic. One of the more difficult things about them is that there's not much in the way of preparation one can do in class about the specifics of a data analysis question. You just have to become familiar with a variety of them. Typically they're going to involve at some point or other looking at a graph and calculating a gradient and trying to figure out what the physical meaning of that gradient is. Let's have a look at this one. The question is about investigating a fireball caused by an explosion. When a fire burns within a confined space, the fire can sometimes spread very rapidly in the form of a circular fireball. Knowing the speed with which these fireballs can spread is of great importance to firefighters. In order to be able to predict this speed, a series of controlled experiments was carried out in which a known amount of petrol, stored in a can was ignited. The radius r of the resulting fireball, produced by the explosion of some petrol in a can, was measured as a function of time t. The results of the experiment for 5 different volumes of petroleum are shown plotted below. Uncertainties in the data are not shown. So we've got 1, 2, 3, 4, 5 separate lines here for different amounts of petroleum. So the petroleum's been put inside of a can and then ignited. And so if you have 5 times 10 to the power of minus 3 cubic meters of petroleum, then over the course of the explosion, which is measured up to somewhere between 60 and 70 milliseconds, you're going to get a fireball that follows this curve in terms of its size. So it gets up to a maximum radius of, 10, 11, 12, 13 meters in radius. Okay, and that's after 64 milliseconds. Okay, and so that's how we read this graph. The fireball, when first ignited, is it should be of 0 size, but it's not quite 0 size. So there's some sort of error going on here, a systematic error of some kind. We can talk about that later. But if you have more petroleum, clearly we're getting larger fireballs each time. So for every amount of time, the more petrol you have, the larger the fireball you have. Okay, so now that we've interpreted the graph, let's have a look at the questions. The original hypothesis was that for a given volume of petrol, the radius r of the fireball would be directly proportional to the time t after the explosion. State 2 reasons why the plotted data do not support the hypothesis. First thing to say is that this is a very typical IB question. They love to talk about direct proportionality. And so over here I'm going to write my answers. The 2 things that you need to know for direct proportionality are that the curve is not straight, and so that doesn't support the hypothesis that there's direct proportionality. In order for things to be directly proportional, you need a straight line graph. And the second thing is the lines do not pass through the origin. And so because they don't pass through the origin, they're not directly proportional. Now sometimes in IB physics we talk about proportionality, and so things can be inversely proportional to the square of, but IB physics really, if they use that term proportional, that's a substitute for directly proportional. And so you can interpret anytime the word proportional is used to mean directly proportional, and that should mean a straight line, and it should be going through the origin. And in this case we have neither of those situations being obeyed, so for that reason we say the plotted data are not supporting that hypothesis. Let's have a look at part B. The uncertainty in the radius is, give or take, 0.5 meters. The addition of error bars to the data points would show that there is in fact a systematic error in the plotted data. Suggest one reason for this systematic error. So systematic error means that all of the data points would be off by the same amount, roughly in the same direction. And the reason for that, well, there could be any number of reasons here, but probably one of the best is that the original experiment was conducted with the petrol stored in a can, and so because it was stored in a can, well, that can's got non-zero volume, and so you're starting with whatever the size of the can is. And so that would be the reason why you're not getting the lines going through the origin, you're not getting direct proportionality. You might not think of that during the exam, so it would be reasonable to say words to the effect that it's hard to measure the size of a fireball. So we might want to just write that down. Hard to measure the size of a fireball's radius. Perhaps it's not a perfect sphere. It could be close to, but I still think that the most common sense answer is that the original can has non-zero volume, and this appears as a non-zero radius when there is no fuel. Okay, and so at the beginning of the experiment over here, at 0 time, we have some non-zero radius, and that's your systematic error. Okay, down to part C. Since the data do not support direct proportionality between the radius r of the fireball and time t, a relation of the form r equals kt to the power of n is proposed, where k and n are constants. In order to find the value of k and of n, the logarithm of r is plotted against the logarithm of t. The resulting graph for a particular volume of petrol is shown below. Uncertainties in the data are not shown. And so now we have a straight line, and this is called linearizing your data. And so if we have a curve given to us, then perhaps this curve follows some power law, and if it does, then taking the log of both quantities allows you to have a straight line, and then you can calculate the gradient of the straight line. And so they're following the recipe for IB physics. Use this graph to deduce that the radius r is proportional to t to the power of 0.4. Explain your reasoning. Okay, this is a little bit mathematical here. So let's have a look at how we might go through this. I'll just move this onto the next page down here so I can type a little bit. So here's our graph. Question being, use it to deduce that the radius r is proportional to t to the power of 0.4. So r is equal to k t to the power of n. Now, if we take, sorry, I just have to get rid of my subscripts there, the logarithm of both sides, so if r is equal to kt to the power of n, then the log of r is equal to the log of that entire function, kt to the power of n. All right, now a little bit of maths. In fact, I'll just move that down to here. All right, so hopefully we're happy with that first little bit of working there. All right, so we're going to say that that is equal to, now if you know your log laws, we can say that's log of k multiplied by, that's not a decimal point, that's multiplication, log of t to the power of n. All right, and then that is equal to, again, log laws know that if you take the logarithm of an exponent, logs and exponents are exchangeable, then the exponent n comes to the front. So we have n log t. Hopefully that's making sense to people. Let me put brackets around this to make it a little bit clearer. So we've got now log of t. All right, so I've gone from log k multiplied by log t to the power of n to log k multiplied by n log t, and that's just the log law. Okay, log of a to the power of b is b log a. Remember that? All right, moving on. The next little bit is if you've got log of A multiplied by log of B, then that is log of A plus log of B. You can switch between those two. So we have now log of K plus N log T. And just rearranging that, so I'm going to put N log T first plus log K. We have the whole formula becoming log of R equals N log K. Okay, so log of R equals N log T plus log of K, and that kind of looks like y equals mx plus b. It's of the form y equals mx plus b. In other words, our y-axis is log of R, and our x-axis is log of t. So our m, the coefficient in front of log of t, that's the gradient. So n's the gradient. Okay, so if I can calculate the gradient of this curve here, this line rather, if I can calculate the gradient of that line, then I'm going to get the number n. Alright, so if I can find what n is, then I can answer the question showing that R is proportional to t to the power of 0.4. In other words, I'm looking for an n that's 0.4, and we're going back over here where the original formula was R equals kt to the power of n. So I'm looking for an n to be 0.4, and we've just shown that n is actually the gradient of this straight line graph. So that's the value I'm looking for. So let's try and do that. The gradient m is equal to rise divided by run. We'll do this calculation, and so I'm going to say that on this graph here, the maximum sort of point that I'm interested in looking at is about 1.22. I'm going to draw a triangle down here and across to here. Okay, so see where my arrow's going there. And so the highest point I'm going to look at is 1.22, and the lowest point here is 0.91. I reckon the intercept there on the y-axis is 0.91. So I've got y2 minus y1 over. Now my x2 point here is 1.8. Okay, so I'm looking at 1.8. I'm not quite going to the end of that line here. I'm just going to where it crosses the 1.8 there. So I'm going to say 1.8 take away 1.0. 1.0 is here on the x-axis. So we've got y2 minus y1 over x2 minus x1. Little triangle there. You can draw it in yourself on your paper. And you will find that if you do that on the calculator, 1.22 take away 0.91 divided by 1.8 take away 1.0, you end up with, on your calculator, 0.3875, and by happy circumstance that's approximately 0.4 as required. So maybe you want to say a little statement in English here. So because the gradient is 0.4, n equals 0.4, and so by the original formula given, R equals k t to the power of 0.4. Or, another way of saying that would be R is proportional to t to the power of 0.4. And there's our 4 marks, I'm presuming. Alright, let's move on now to part D, where it says, it is known that the energy released in the explosion is proportional to the initial volume of petrol. A hypothesis made by the experimenters is that at a given time, the radius of the fireball is proportional to the energy E released by the explosion. In order to test this hypothesis, the radius R of the fireball 20 milliseconds after the explosion was plotted against the initial volume V of petrol causing the fireball. The resulting graph is shown below. Okay, so we've got a number that's been given here. This is where you really need to read the question carefully. It's sometimes hard to notice the relevant information here, but there's a number that's been given there, so that should hopefully stand out to you. It's a time, okay, milliseconds. There's no time on this graph. Well, let's read on and see how we might include that time. The uncertainties in R have been included now. The uncertainty in the volume of petrol is negligible. Describe how the data for the above graph are obtained from the graph in A. Okay, so let's go to the graph in A, and we've got a bunch of curves. So we've got a time axis here. We're looking at the 20 millisecond time. So at 20 milliseconds, we've got our different curves here. So words to the effect that the graph down here has been arrived at by looking at the previous graph, by looking at the 20 millisecond intercept, okay, the X line, drawing a vertical line up from 20 milliseconds, which is what we do over here. So drawing a line up from 20 milliseconds and seeing where it intercepts each of those curves. And where it intersects each of those curves, we merely need to read off the relevant radius. Okay, so let's try and put that into natural language. I would probably say something to the effect of how do we say that? So answering this first part here, just above the question, I might say for the original graph in A, construct a vertical line at 20 milliseconds up to where it intersects each of the curves and read off the relevant R value to construct this graph, this new graph. Okay. Draw a line of best fit for the data points. Okay, so it's not going to be a straight line, but your curve needs to be smooth and it needs to go through all of the error bars. Okay, so I actually reversed engineered this, by which I mean I did it once by using a pencil and going through it on a piece of paper, and what I found is that I didn't get what I should have got. Now, I knew that I'd made an error, or what I think was an error, because we're going to get to the last question where the y-intercept here, where this curve that you've drawn, the best fit curve, intersects with the y, the r-axis here, it makes a difference. And so if you're drawing that curve and you extrapolate, do you extrapolate down here? Do you extrapolate to here? Do you extrapolate to here? It's hard to tell. So it's important to use a pencil because you just might need to erase things. On the other hand, you could just try not to do that and connect this dot to this dot smoothly. Okay, you could reasonably do that and not extrapolate, but you kind of need to extrapolate, and let's see why. Part 3, explain whether the plotted data together with the error bar support the hypothesis that R is proportional to V. It seems to me that this is a silly question. After all, we've just been asked back here, you know, are these curves here proportional? We said no, because they don't pass through the origin, number one, and, well, they aren't straight. Precisely the same answer here, so we're repeating ourselves. So the answer to this question, part 3, does this data support the hypothesis that R is proportional to V? No, they don't. The data doesn't support that because we can't draw a straight line through all of the error bars. Okay, so it's not a straight line. And number 2, it's not going to pass through the origin either. So there's our 2 marks again. Same question, repeat question. Alright, so that's part 3. E, analysis shows that the relation between the radius r, energy E, released, and time t is in fact given by r to the power of 5 equals E t squared. Use data from the graph in D to deduce that the energy liberated by the combustion of 1 times 10 to the power of minus 3 cubic meters of petrol is about 30 megajoules. Okay, so 30 times 10 to the power of 6. The way that the official mark scheme wants you to answer this, to respond to this, is to pick a point, say 10, and to substitute relevant values, okay, and then because we've got, say, 10 times 10 to the power of minus 3, and we've got this data point here, so we can do an estimate by getting r. So we've got a 10, we've got a value for r, then we can find E. And then having calculated E for 10, let's say, we then divide by 10 so that we can get 1. Okay, so here's the last part of the question, part E, where it says analysis shows that the relation between the radius r, energy E released, and time t is in fact given by r to the power of 5 equals E t squared. Use data from the graph in D to deduce that the energy liberated by the combustion of 1 times 10 to the minus 3 meters cubed of petrol is about 30 megajoules. And as I was saying, the suggested technique in the sample answers I personally don't think is a valid one. What's going on there is that they are saying that you should choose, in D here, a particular point. But the problem there is that the value that you ultimately get for the amount of energy that's released by a given volume depends entirely upon the point that you choose. And so you'll get a different value for if you choose this point compared to this point. And for whatever reason, the official answers from the IB say to use a value for V between 5 and 15. I'm not sure if that's a misprint, if what they actually mean is a value of R between 5 and 15, which would include all these data points, or not. But using their particular technique, what they say is, well, pick a value, and they've picked up here, they've picked this particular value here. And that point there, they picked this second point here. This second point here is 10.5 is the radius and 10 is the volume. And so having picked that particular point, you work through and you do this. So for R equals 10.5 and V equals 10, substitute those into the equation here. So R equals 10.5. Now, all of the experiments in that graph D are done at 20 milliseconds. So that's how we know that our T in this equation here equals 20 times 10 to the power of minus 3. And so we have 10.5 to the power of 5 divided by 20 times 10 to the power of minus 3 all squared to get a value of the energy of 320 times 10 to the power of 6, which is around about 300 megajoules. That's for a volume equal to 10, but we want a volume equal to 1, so therefore take that number there, divide by 10 to get about 30 as required. Now, my issue here is that they seem to have fudged the figures. They seem to have fudged the figures because if you then choose not to use that value, but instead decide to use this value here, so this is the value corresponding to V equals 15, and V equals 15, if you go across, that's actually 11.75. It's in between these two boxes here. So that's an R of 11.75, a V of 15, all happening at 20 milliseconds. And we can substitute in this way now. So we get 11.75 all to the power of 5 divided by 20 times 10 to the power of minus 3, which equals 559 times 10 to the power of 6, which is 560 megajoules at for 15, for a volume of 15. So divide that number by 15 to get 37 megajoules for 1 litre. Now, that doesn't seem to me to be approximately 30 megajoules as required by the question. I think there's a problem with the question, okay? That entire process is invalid. What we should notice is that the question of how much energy is released is really a question about how much energy you're getting for a single, so for 1 times 10 to the power of minus 3 meters cubed, how much energy would be produced by burning that much fuel. Now, if you're burning 30, a volume of 30 times 10 to the power minus 3 meters cubed in an enclosed space, which is how the entire question here started, then you might not be getting incomplete combustion. But in that same space, if you're burning 1, okay, and so for 1, that's the very first line here on this graph here. Okay, we don't have a data point there, but we could extrapolate. And we notice that it's a curve, and so it's going downwards. The only way that you can use the technique is that is provided by the IB is if you had a straight line. Okay, we don't have a straight line. We explicitly went through a whole process talking about how there was no straight line. So if we were to extrapolate this, okay, we'd end up drawing a line down here somewhere, and in fact I've done that. So this is what such a graph would look like. So if you do your nice smooth curve between here and here, and then if you extrapolate that line, it's roughly there, but it's hard to tell, right? We don't know whether it actually intersects the y-axis or the r-axis here or down here. We don't know where. I've done a best guess, okay, and assumed that it's going around about there, somewhere above the 5. Does it intersect the axis there? Now, in truth, when you've got a 0 volume of fuel, you should have a 0 radius of the fireball. Yeah, that's obvious. That much is clear. But because of the way the experiment was done, we know that the radius isn't equal to 0 when the volume is equal to 0 because the container that we put it in actually has a certain volume. All of that said, my extrapolation suggests that when you have V equal to 1, okay, the corresponding R value here then is 6.5. So let's see what happens there. So if I extrapolate the graph so that I get an R of 6.5, then it becomes 6.5 squared. That's my R to the power of 5 equals E times 20 times 10 to the power minus 3 all squared. Now if I use that expression to figure out E, I end up with an E of around about 29 megajoules, okay? 29 million, no, sorry, not, yeah, 29 million megajoules. 29 million joules, which is 29 megajoules. And that's extremely close to the 30 megajoules required. But the problem with that process is, of course, we don't know where the intercept here is, okay? Really, it should be down here, but it's a systematic error, so it's not, it's up there somewhere. This is all a bit of a fudge, okay? So it's a bad question. Not only is it a bad question, but the suggested answers are wide of the mark. The best way of answering this would be using an extrapolation graphical method, but even that has flaws. This is what you might need to expect sometimes. Sometimes you just have to do your best with what you've been given. I would presume that in the actual marking of this, that either of these two techniques would have been permissible, and if you didn't get exactly near the 30 megajoules, because you used some other data point here to substitute values in, then you couldn't very well be penalised for that. And that's the end of that question.